Welcome everybody to the final meeting in fall 2021 of the CEDAR Risk Seminar. Of course, you all know me, I'm Ms. Goldberg, and who you don't know, I guess, is our speaker talking on a really exciting topic for me, for sure. Iordanis Kerenidis of Ware, Prospects and Challenges of Quantum Finance. So Iordanis, I'll go on mute and you take it away.
Perfect. Thanks, everyone. Thanks, Lisa. I'm really happy for the invitation and being able to speak here. It would be even better if I was actually in Berkeley. In fact, I'm not very far because I am visiting Palo Alto, but you know, it's still a period where seminars are happening through Zoom. So I hope it's going to work well. And let me start by sharing my screen and then we can start. Okay, so I hope you can see my slides. So what I wanted to do is give you some sort of high-level description of what quantum computing can do in finance, right? So as Lisa said, I have been working on quantum algorithms for more than 20 years now. I did my PhD in Berkeley, then I was at MIT, and for the last 15 years, I'm based in Paris. I'm a research director for CNRS. And for the last couple of years, given that, quantum computers are starting to exist, slowly, I'm working with Ware, which is a startup working on quantum algorithms. So we're not doing hardware, we're not building quantum computers, we're trying to understand what kind of applications these new machines are going to have. And finance is one of the areas where we think that quantum computers can actually be quite interesting. Okay. So I'm going to talk about three different areas. I will talk more about the first two. One is Monte Carlo methods for stochastic processes, right? It could be interesting for finance, but for many other things, you have all these kind of stochastic processes that model some system and you want to simulate them and figure out some sort of expectation or some observable, and we will see what quantum computers can do to help in this type of tasks. And the second is that we will go through different machine learning methods, whether for supervised or unsupervised learning, a little bit also for reinforcement learning. And again, there I would like to give you what are the core things that the quantum computer could actually do, let's say, better or faster, and how they can enhance all these machine learning methods that we have. And at the very end, I will talk a little bit about portfolio optimization. And speaking with Lisa, like just before the talk, I just added a very last slide as well. I'm discussing a little bit about security issues and what are the bad things that could come from quantum computers when it comes to security of financial transactions and things like that. I hadn't prepared for that, but I'm happy to discuss it as well. Okay, so I have here a link to one of the papers that we wrote recently. It's more like a survey on prospects and challenges of quantum finance, where you can find mostly, again, these three main categories of problems. And I want to start by saying, why do we care about quantum, right? So I think one of the main things that we need to understand is that a quantum computer is not a faster processor. So it's not like the next generation of a high performance computer, which we will be able to use the same way we use now our HPC machines or our GPUs. It's actually a fundamentally different way of performing computation, right? That can be much faster for certain tasks. Okay, so there are many tasks where a quantum computer cannot offer any advantage with respect to a classical computer, right? We can actually prove mathematically that for certain problems, the power of a quantum computer is exactly the same as the power of a classical computer. But at the same time, there are other tasks where we can also mathematically prove that a quantum computer could solve them much, much faster, sometimes exponentially faster, sometimes polynomially faster than on a classical computer, okay? So what this says is that the quantum computing will not replace classical computing, right? But we do expect it to remove some computational bottlenecks that we have, and hence open the way to some new applications. And this is why we need to start rethinking and reinventing new algorithmic solutions. So there is a lot of work to be done on the algorithmic side, because as I said, these are some hardware machines, some new hardware machines that work in a very different way. And we need to start understanding how to take advantage of this power that comes from encoding information and computing with these quantum mechanical systems. Okay. So I wanted to start by looking at Monte Carlo methods. Then I will talk about machine learning, and at the end about optimization. It's something which is which we have been working a lot in these methods. We are working also with people like Goldman Sachs and other financial institutions. And we came up with a couple of papers. One is from last December. The other was actually from last month. So these are kind of very new results. And I want to explain in high level and without assuming much background on quantum, what is it all about? Okay. So we kind of know that Monte Carlo algorithms have a lot of applications, also in finance, things like derivative pricing or risk analysis. And the basic idea is very simple. We want to estimate some value, let's say the risk neutral value of a derivative. And how do we do it? We run a market model many, many times, and we compute some expectations, some mean value, right? And what we know very well is that the number of times we need to run this model kind of grows with respect to the accuracy that we want in the end. And if we want to estimate this value up to an accuracy epsilon, then we have this well-known result that we need 1 over epsilon square runs of our market model, right? And in many times, especially, of course.
Yeah. So, I mean, if you're in the Black-Scholes model, you've got a formula, so there's no reason to do that. So I'm assuming you're outside it, but then what type of model are you using, or how do you set the parameters of the model first?
So let me use the model as like whatever black box commutation you want to do. Like maybe you want to do a geometric Brownian motion, right? And take a path of prices or some Levy process or some other stochastic process, right? So what I will talk in the first part of the talk will be kind of independent of how you want to model your market or your thing. And then we will also try to go a little bit inside as well and figure out if we can do something actually in sampling from the stochastic processes. But let's say for now you have some stochastic process. For example, let's say you want to do something simple, right? Let's say you want to price an Asian option. So I need to understand, I need to take many paths of a price of a stock for a year, and then I need to have this computational path and then do many times so that I can come up with a price at the end, right? So basically what we are saying is that the number of how many samples you need to take is a very well understood thing. And sometimes, especially if you want very good accuracies or like Ware or CVAR computations, then it might be that you need to run this model actually thousands or even a million times, let's say. Okay. So here is what a quantum computer can do, right? And again, I'm describing it in a very kind of black box way. What we know from like more than 20 years, like roughly 20 years ago, is that a quantum computer can do exactly the same, like estimating some sort of price or some value up to an epsilon accuracy. But now the number of samples that we need to take from this model is not 1 over epsilon squared, but it is 1 over epsilon. Okay, and I will explain a little bit more how this algorithm works. But the idea is that in theory, if I give you a full perfect quantum computer that has as many qubits as I need, then you can get this speed up in some sense on the number of samples that you need to take from this model in order to estimate whatever, the value that you want to estimate, right? And, for some epsilons in the range of 10 to the minus 3, 10 to the minus 4, you can see that theoretically you can get this 1,000 times speed up with respect to running the classical Monte Carlo methods. Okay. Now, this is not the end of the story, because this is what a perfect big quantum computer can do, but this is actually not a very easy algorithm to run on a quantum computer, right? And in fact, the main bottleneck for this application of quantum computer is that actually the way that the algorithm works is not that you have to independently take 1/epsilon samples, the same way that classically you just take 1/epsilon square independent samples, where you can even think of parallelizing them or doing them, in different cores or things like that. But it's a more complicated algorithm where you have to do this 1/epsilon samples in sequence in some sense. So basically you have this quantum circuit that kind of simulates your stochastic process. And then what you do is that the output of the first time that you run this market model should be the input to the second time you actually apply your model, and the output will be the input to the third time. So you have to do this 1/epsilon kind of runs of your model in sequence, and having to keep these qubits alive for a very long time because you have to go through all of this simulation. The bottom line is that we need very, very good quality qubits if we want to actually do this 1/epsilon times sampling of this quantum Monte Carlo method. Okay, and this is why what we are saying is that in principle, this is not going to be, let's say, the first application of quantum computers for finance, because again, what we were seeing is that you will need this very good qubit quality, and I will show you a little bit some numbers to get a feeling of where we are and where we need to go. Okay. So what we developed a couple of months ago is basically something quite simple that says the following, right? So as I told you, if we want to get this 1/epsilon speed up, let's call 1/epsilon 1,000, right? If you want to get this 1,000-fold speed up using a quantum computer, then what you need is to use this very, very complicated, let's say, quantum circuit that has 1,000, that the depth of the circuit, let's say, the depth of the algorithm is of the order of 1,000, because you need to do these 1,000 market models one after the other. So what was interesting to notice, though, is that we can actually come up with let's say, simpler quantum algorithms that kind of trade off two things. They trade off what is the speed up that they offer, okay, with how difficult it is to actually implement this quantum algorithm. Okay, and what we saw is that something that, a posteriori you could imagine that it is true, that says that if I needed to get the speed up of 1,000 times, then I needed a 1,000 deep quantum algorithm. But if I just want to see a 10-fold speed up or a 100-fold speed up, then the complexity of this quantum circuit is much smaller. It's actually 10. The depth would be like 10 or 100. So somehow you can start seeing speed ups, which may not go all the way to 1,000, but you can start seeing it with quantum algorithms that necessitate much fewer qubits and much less quality qubits. So why are we doing all this? The reason we're doing all this is that we don't have quantum computers right now, right? It is very difficult to build quantum computers, but we have started seeing some quantum machines, I would call them, that have a limited number of quantum bits and they're very noisy. Okay, so the main question that we ask is, can we actually use these noisy quantum machines that are starting to appear now or that will appear in the next 2-3 years, or do we really have to wait until we have the perfect quantum computers that may arrive in 10 or 20 years? Okay. So kind of this is an example where we can say that we can bring the timeline of these quantum applications much closer to us, because we can start seeing some speed ups when it comes to Monte Carlo methods with quantum machines that don't need to be perfect. Okay, so here are some numbers just to see where we were before and where we are with this new type of algorithms. So these numbers here are some very simple number that says how many operations do I need to be able to do in a quantum computer without an error in order to see a speed up with respect to the classical algorithms, right? And we have kind of made different computations for, let's say, different types of derivatives. Simple derivative would be something like a European option, right? Which, okay, as Bob said, you don't even need to do, let's say, the Monte Carlo, you can just do the Black-Scholes, but some sort of simple derivatives. Then you have moderately complex derivatives and then highly complex derivatives. And the difference between this is how difficult it is to actually implement your model, right? Even once, to sample once from this. And what we had before is that the number of operations that you should be able to do without any error in a quantum computer was something like 10 to the 10 or 10 to the 12, which is very, very big number, right? You really needed qubits which never make an error, let's say. And what these new algorithms did is that they managed to reduce the quality of the qubits that we need to something like 10 to the minus 5. So you need to be able to do 100,000 computations in a quantum computer without having an error, let's say, with high probability. We are not there yet. Like the quantum machines that we have nowadays, they have something like, they can do something like 1,000 computations without an error. And then errors start happening, a noise, and then what you get is some noise at the end that you cannot use to do something like a Monte Carlo simulation. But we are not that far as we were before, right? So we went from something like 7 orders of magnitude before to we need another 2 or 3 orders of magnitude still. Okay, so it will still take some time. So I want to be very clear right now. Quantum computers today cannot do anything that you cannot do much better with your classical computers. This is the case. But while as the hardware will advance and as we will be having more qubits and better qubits, we will be start seeing these quantum advantages happening also for finance applications. Okay. Okay. Any question on that? What I will try to do is try to explain a little bit with pictures and then a little bit with math how this algorithm works without going into any of the quantum details. It's fairly simple way to understand things, and then we can discuss a little bit this part before going to the machine learning. Okay. Okay. So here is in a black box manner how this Monte Carlo and quantum Monte Carlo work, right? Let's say you have some way of sampling from some sort of stochastic process, right? And what would you do? You want to be able to do this on a quantum computer. So you take the way that you're computing your stochastic process, you can kind of map it into a quantum circuit. Let's say we know how to do this. Okay, so then what do you do? And I will come back to the question that was asked in the beginning. Can a quantum computer help in actually being able to sample faster from the stochastic processes? Okay, so actually, let me say a couple of words here. So imagine I want to create a path of length 100 of a Brownian process, right? So what do I do classically? Classically, I just, I go step by step and I take 100 steps up and down to create a single path of this stochastic process, let's say. Okay, I'm simplifying a bit things, but okay. So now the question is, can we do something interesting if I give you a quantum computer to create again this kind of paths from the stochastic processes? And the answer is yes, right? So I'm doing kind of a side thing here. So, for example, there is let's say, one of the very powerful things that the quantum computer can do is actually do the Fourier transform. Okay, what do I mean? I mean that there is a quantum circuit that very fast, actually in logarithmic number of steps, can take something from the time domain to the Fourier domain and back. Okay. Now, why is this interesting for the stochastic processes? If we look at something simple like a Brownian motion, for example, it is very interesting to see what happens if we look at it not in the time domain, but in the Fourier domain. Okay, and what we see there is that the spectrum is actually very, very concentrated. There are very few big Fourier coefficients, and then they very fast drop exponentially towards 0. Okay. So here is one way of trying to create a classical algorithm to create this Brownian paths, let's say, which is not interesting classically, but it will become interesting in the quantum sense. One thing that you would want to do is, for example, instead of creating this path in the time domain, you look at its spectrum, okay? You compute these Fourier coefficients, which are not many. There are some constant number, let's say like 100, okay? This gives you a very good approximation of what the t path would be once you take it from the Fourier domain to the time domain. And then you apply a Fourier transform into this, and this gives you the equivalent, let's say, of a time path on the Brownian motion, okay? Why do you not want to do this classically? Because taking this transform, this Fourier transform, it takes actually n log n time. It's actually even more, a little bit more than linear on the time, so you might as well do it faster in the time domain to start with, okay? But now, as we said, what a quantum computer could do is actually perform this back and forth between the time domain and the Fourier domain in logarithmic time. So what you can do as a way to create this time Brownian paths is to start by computing this small number of Fourier coefficients, okay, and then do a fast quantum Fourier transform on the quantum computer. And what the output of this thing will be is exactly what you were doing in the time domain, some sort of stochastic path of this process, right? But now the time that you spend is not linear on the time steps or on the let's say on the length of this path, but only logarithmic on the path, okay? So this is also something that we've been working on, and it's a way to kind of efficiently sample from these models. We don't know how to do it for all stochastic processes. We are starting with the simple things, including, you know, as we said, the Brownian motion or the geometric Brownian motion, things like that, okay? But to be honest, I think this these techniques should extend to more complicated stochastic processes, as long basically to all processes where there is something interesting to say about the spectrum, the Fourier spectrum of these processes. Okay. Okay, sorry. So that was a side thing of what do we do with the models, with the stochastic processes themselves, right? But now let's go back a little bit on how many samples do we need from these processes, right? And as we said, classically, what we do is that we independently create many of these paths, and then we aggregate the results and we output the expectation, right? And we know exactly how many we need. We need something like 1 over epsilon squared. As I said, what the quantum thing would do is basically join these things, not in parallel, but sequentially. So there is this very long quantum process that takes this 1 over epsilon now and not 1 over epsilon squared, modeling circuits one after the other. And what you do is that you only measure something at the very end of this quantum circuit, okay? So the depth of this quantum circuit is now 1 over epsilon, but the number of samples that you need is actually 1. You can, what you, somehow at the end of this quantum circuit, what you're sampling from now is actually the expectation of this 1 over epsilon market models calls, and this is exactly what you need to get this epsilon accuracy. So as I said, the problem with this is that there is this very, very long quantum circuit that we don't know how to implement now, right? So there is a gap, there is a frontier on how deep quantum circuits we can do because of, you know, how good quality qubits we have, okay? So what happens if we can only do it, let's say, 3 times, but not 1,000 times as we would do it, right? So the first thing you could imagine is to say that, okay, what if I in parallel now do these shorter quantum circuits? This doesn't work, but something similar to that actually works, right? So what you need to do is basically start using different depth quantum circuits, okay? You get different samples, and then you don't aggregate the samples in a simple way, as in let's sum them up and this will give me the expectation. You have to do a maximum likelihood expectation on these different outcomes in order to get a very good accuracy, very good approximation to the expectation. Okay. And if you want to see it, and this is my last slide on the Monte Carlo, if you want to see it a little bit more in a way that it should be very clear to you, you know, classically, what do we do? Let's say simplest thing, we're sampling from a Bernoulli variable with some success probability P, which is some cosine square theta. And every time we flip this coin, we pay 1, let's say, right? Because we're counting the number of samples. And then we know very simply how many samples you need to get epsilon close to this theta parameter. So what the quantum Monte Carlo allows you to do is that somehow it allows you not only to sample from this Bernoulli variable that has probability cosine square theta, but by doing this thing sequentially, you can also sample from cosine square 3 times theta or 5 times theta. And at the very end, you will be sampling from something like cosine theta over epsilon, okay? The cost increases as well, right? To sample from cosine square 3 theta, you need to pay cost 3, right? But somehow the fact that you are sampling from not only theta, but also these multiples of theta, if you really do the computations and you look at the Fisher information and you figure out how to combine all of these things together, this is where you can get this speed up by saying that by computing that you only need 1 over epsilon sample from these higher multiples of theta and combine these results in an interesting way to get this epsilon accuracy that you need. Okay, and when we talked about the shallow quantum Monte Carlo, which is the ones that we hope we can implement in the next few years, then you don't go all the way to the depth 1 epsilon, but you cut the depth with some parameter there, beta, and then these kind of trade-offs, how deep you need to go and how much of a trade-off you get. So these are the 2 papers that explain more about these things. One is called the low depth algorithms for quantum amplitude estimation. Amplitude estimation is this algorithm of estimating some amplitude or some expectation in this more efficient way quantumly. And we also performed an experiment on real quantum hardware from a company called IonQ. And we saw actually, that if we were sampling directly from the quantum, from the market, from the model, let's say, from the oracle, and try to compute the expectation, we would get worse results than if we would actually apply these longer quantum circuits and we will combine the outcomes of these ones to get the expectation. So we kind of show that even the computers right now can apply this algorithm, but the model was a trivial model that was actually not corresponding to anything that you would like to do to price a derivative or some option and things like that. So right now we have to use very few qubits and very short circuits, so we cannot quantumly sample, let's say, from any interesting model or any interesting stochastic process, but it's a matter of time, let's say, on when the hardware will catch up somehow. It's the same as we were saying with the neural networks. The theory is there, the math is there. We are just working towards reducing the resources that we need, so the hardware will catch up faster with the hardware will catch up with the algorithms sooner. Okay. Maybe I take a quick break here to see if there are any questions on the Monte Carlo and stochastic processes part.
Sorry. Hi, Iordanis. I have a question. My name is Robert. If you go back 1 or 2 slides where you were right here. Mm-hmm. So we have the classical on the one hand side, and now on the right hand side we have the quantum. And I see that you're running this sampling for different values of the argument in the theta, and you have cost 1, 3, 5, and so forth, up to 1 over epsilon. So if you add up all the costs, that's going to be quadratic in 1 over epsilon, right? The sum of first n integers up to n is n squared. Except if you run this in parallel, then it's just the maximum, which is 1 over epsilon. Is that what's happening?
So what's happening is that here in the quantum algorithm, if you can go all the way to the theta over epsilon, right, then you only need to run the last line. You don't need to sample from the previous things.
Oh.
Okay, so if you can go to theta over epsilon, meaning that you have this quantum circuit that has depth 1 over epsilon, then basically sampling directly from this cosine theta over epsilon will give you the accuracy that you need without having to go in the previous ones. If you cannot go all the way to 1 over epsilon, right, and let's say you can only go to epsilon 1 minus, let's say epsilon with a half, 1 over square of epsilon, then it's not enough to just sample from this one. You also need to be sampling from some previous steps, okay? So that when you do the maximum likelihood estimation, you can actually get the correct answer, okay? But you're right, the way I wrote it here, if you had to do every single step separately, then you are sampling 1 over epsilon square times, right? But here, if you can do this last part, then it's enough to just sample from that one.
Okay.
Okay.
And so if you can do this last one, right? How many samples do you have to get? How many times you have to run the quantum computer through that?
This one. So if you just run
once?
this guy just once. So what you do at the end, you get log 1 over epsilon bits with the expected value written into this log 1 over epsilon bits, right?
Oh, okay.
And the guarantee that you have is that with very high probability, these are the correct log 1 over epsilon bits. So you are epsilon close to the real value that you are trying to estimate.
Okay, thank you.
Okay. Any other question? Okay, so let me try to go through a few things on the machine learning part. So what do we know now about quantum machine learning? Obviously, quantum machine learning and machine learning is something much more general that one can use in, pretty much everywhere now. But, I will focus a bit more on why is it interesting on, things that have to do with risk calculations or other finance problems, right? So what do we know about quantum machine learning, right? So the first thing we know, again, we start with a similar thing as we were starting with the Monte Carlo. The first thing we know that if we had big enough quantum computers, then we can mathematically prove that these quantum computers can offer big advantages in certain applications of machine learning. Here are some of them. I'm not going to talk about all of these. These are some of the papers coming out from Ware and my team at the university in Paris. So they have to do with classification, with clustering, with recommendation systems, with also a little bit also with neural networks, but there we have to be a little bit more careful. So I will tell you a little bit about the neural networks as well, but also in the more optimization, like convex optimization part, like how do you do linear programming, semi-definite programming, all these kind of interior point methods. This is also some very interesting results there that are also useful. So I just wanted to show you that, we can prove that if we had, or when we will have the quantum computers that we need, we can offer big advantages. And the main tool here that the quantum computer can do is actually linear algebra. Okay, so what we can do faster, let's say, in a quantum computer are things that have to do with, let's say, I give you a matrix, figure out something about the eigenvectors and the eigenvalues of the matrix, or find a good low-rank approximation of the matrix, or project on the top k eigenspace, things like PCA, or do spectral clustering, compute the Laplace. So anything that has this more hard, heavy linear algebra things, all of this n to the cube kind of algorithms that we don't use in practice too much, because the moment the data becomes a little bigger, cubic algorithms are not very easy to use. So these are kind of the places where a quantum computer can help, right? So it's quite powerful because it can speed up some very core computations in many different machine learning applications. But we also have to be very careful because it's not so black box results, like no matter what your model is, I can sample, I can do Monte Carlo with fewer samples. No, here there are these quantum algorithms that have to do with linear algebra, where whether you get a speed up or how big a speed up you can get actually depends on the data. Okay, so for example, things like I give you a linear system of equations and you want to solve the linear system of equations. So you need to invert some matrix, right? So whether a quantum computer can do this faster than a classical computer depends on some properties of this matrix. Like, is it well conditioned, or do you have very tiny, eigenvalues? Is it sparse, or is it low rank, or, some sort of properties of the matrix themselves? We know exactly what the quantum running time of the quantum algorithm is. It's just that the running time depends on some parameters that are specific on the input. And depending on the input, sometimes this running time is better than the n to the omega or n cube classical algorithm. Sometimes it can be as bad as that, right? So for the worst case, it will not give you any speed up. But for many interesting cases, we do see that you should be getting speed ups with respect to the classical algorithms for this heavy duty linear algebra.
That's the question.
Sure.
So yeah, one of the big advances in numerical linear algebra over the last 10 to 15 years has been randomized methods. So
yeah.
you pick a set of vectors at random, you then can quickly solve the process, and there are theorems that guarantee that with high probability your answer is some tolerance from the best bound. Is this connected?
Yeah. So we are looking a lot at all these randomized linear algebra techniques, and many times when we want to compare the quantum with the classical, we have to compare it exactly with these randomized linear algebra techniques. And there are some very interesting ways of doing things over there. Sometimes they provide fast algorithms in practice. Sometimes they are very bad in practice, even though theoretically they have a better kind of performance. In practice, they are not used as much. It depends let's say, on the application. The techniques are not the same. So the quantum case is not about subsampling matrices and doing things in smaller matrices and somehow approximating what will happen in the bigger matrix. So it's not exactly that, right? It's more, again, the same way that I was saying that we can do the Fourier transform fast quantumly. One thing that we can do very fast is estimating eigenvalues corresponding to eigenvectors. So what you will do, for example, when you do this quantum algorithm is running this procedure that very fast can tell you what eigenvalues you have with respect to the eigenvectors. And then you can decide to do things like projections or PCA or things like that. So the numerical linear algebra are extremely interesting things. And there have been actually also some results that looked at the quantum algorithms and then they tried to go back and figure out, can I do a similar thing with randomized techniques without using any quantum? Okay, and sometimes it's possible, in many times it's not. Okay, but we work a lot with the people who are doing this randomized linear algebra things, like Michael Mahoney in Berkeley and Ravi Kannan. So all these people, we look very closely in what they are doing. For example, one of the things that we were doing recently is all these things called determinant point processes, where they use also a lot on, you have a very large data set and you want to pick a diverse subset of users to do something, some like regression afterwards. So what's the best way of picking this subset? So all of these kind of techniques like leverage scores and things are very, very interesting. Yeah. Okay, so the second thing I want to say about quantum machine learning is that on one hand, we know that if we have good computers, there are some applications where you can prove that you can offer advantages. The second thing is that we can, again, try to squeeze as much as we can from the machines that we will be having in the next few years and trying to take this, also complicated quantum algorithms and make them simpler and simpler in order to be able to fit in these machines that will happen. Okay. So we can do simple things like classification and regression. One of the main things here that we use is the fact that if you have two data points and you see them and somehow you have mapped these classical data points, which are like n-dimensional vectors, let's say, into quantum states, okay, then one thing you can do very efficiently is figure out how far apart these quantum states are. So if I give you two quantum states and I tell you, are they roughly the same state or are they orthogonal states, right? Then there is a very fast quantum procedure that tests exactly this thing, okay? And you can see how this is very interesting for machine learning applications, especially all the ones that are based on similarity learning. Like when you want to cluster things together, what you check is, are they close to each other or very far from each other, right? So a quantum computer, let's say, can speed up this process of figuring out distances between data points. I want to be a little more careful here to say that we can speed it up with respect to a CPU that does one operation at a time. We are getting, let's say, similar times as what you would do with a multi-core parallel GPU, right? But then you can also imagine that the quantum processing units can also become multi-core in the future, and you can do things in parallel, let's say, stuff like that. So for now, I'm comparing, let's say, one quantum computer with one classical computer, not multi-core architectures, let's say. And there you can see, you can prove actually a speed up between how long it takes to compute these distances, okay? So I wanted to give you two slides on where are we today, what can we do today in machine learning with the quantum computers that exist, right? So here is one thing that we did a few months ago. We started from the very basics. We looked at the MNIST, these 100 digits, and we said, can a quantum computer distinguish the 10 different types of 100 digits, right? How well can we do it? And how well we could do it is something like 80% accuracy. So it's nowhere close to the 99.9% or 5% that the classical model can do right now, but it's still, on the way from, randomly picking a number which will give you 10%. We can use a tiny quantum computer with 11 quantum bits to get to 80% accuracy. Okay, so there is a way to go, but we are starting to see some non-trivial demonstrations even on the real hardware. Okay, this was a second work that we did on not on final, but with medical images, where there we used what we called quantum neural networks. So what is a quantum neural network is very similar to what a classical neural network is, in the sense that a classical neural network is some sort of a parameterized system with a lot of parameters, which are the weights. And what you do is that you put some inputs, you check the outputs, and you try to learn these parameters, right? So the same way we have these weight matrices that we try to learn in a classical neural network, in a quantum analog of that, you can imagine that you have some quantum parameters. And what you do again is that you put some inputs, you get some outputs, and you want to try to learn these quantum parameters, right? So you can define a similar type of things like a gradient descent on the optimization landscape of the parameters. You can do this backpropagation on other type of learning, and you can try to learn what is the quantum circuit, this parameterized quantum algorithm that will solve this classification problem, let's say. Okay. We can do things like clustering, again, because of these distances. This is something that I briefly discussed a bit before. This is something that we do with a bank. The problem is very simple. They have 2 million customers, and they want to predict whether a customer will go to churn in the next 3 months or not. So I'm not an expert in finance, so I didn't even know what churning is, but I found out. So the question is, how many of these people will take their money out of the bank in the next 3 months? And they want to know this to predict it well, because then they can go and offer them things or talk to them, let's say, or try to convince them. So the question is, you have 2 million users, you cannot go and call 2 million people, and you cannot do many things, even like a simple regression with 2 million, users. The question is, how do you pick a representative, subsample of these users, and then you can use it to train like a random forest or a regression model on that, right? So there are different ways of picking things, and we were looking at this determinantal sampling, right, which is kind of, one can prove that this is the optimal way of doing it when you want to do something like a linear regression afterwards. And the determinant sampling, basically, it's a process where, let's say there is a negative correlation between how close points are picked. So if you already have a point somewhere, then it doesn't pick points which are very close to each other, right? Because they kind of have a negative penalty if they are close to the points which are already picked. So it picks this kind of diverse subset of clients, let's say. And what we saw, even with no, let's say, and the reason we wanted to do these determinant point processes is because we can prove that the quantum computer can take this algorithm, which is a cubic algorithm in the classical sense, and provide a linear time algorithm for this. Okay, so we had this quantum versus classical speed up between a cubic algorithm, classical, versus a linear time algorithm, quantum. We cannot implement this on the 2 million users. We don't have these quantum computers yet. But what we said is that, okay, but can we at least use this idea and go back to, as we were saying, like randomized linear algebra techniques for these DPP processes? Can this improve what they were doing? And actually it can. We improved like 5% their precision, even with classical methods that use this determinant sampling for this churning problem. And what we know is that this is not very scalable in the classical sense, because, as I said, it's a cubic time algorithm. But the moment the quantum computer can come, then you get the best of both worlds. You get a fast algorithm and also a very good and very accurate algorithm for this type of problems. I will skip for the sake of time. I just have one slide on optimization, and then I will conclude. So optimization is kind of everywhere, right? So we have this like portfolio optimization and many different other types of optimization. I just wanted to give you a hint of what can quantum do for optimization problems, okay? So the first type of algorithms, or actually heuristics, that we have is basically analog of the classical heuristics that one uses for all this type of combinatorial optimization problems, things like integer programming or traveling salesmen or max-cut problems. So you have all these kind of NP-complete problems. You use, in practice, some heuristics to try and solve them. We also have some quantum heuristics that try to solve this kind of very difficult problems. They're not going to work always the same way that classically they don't always work. But the question there is, can these quantum heuristics be useful and can be used like in addition to the classical heuristics, and sometimes give you better solutions than what you get from the classical? Obviously, the solutions will not be the global minimum, for example. There will be some local minima, but the question is, can you kind of use these quantum properties to avoid some sort of shallow linear local minima and figure out a good, let's say, minimum. Okay. So as I said, when it comes to combinatorial optimization, these are NP-hard problems. A quantum computer will not solve NP-complete problems or NP-hard problems in the worst case, but we have quantum heuristics the same way that we have classical heuristics that try to solve these problems as well as we can. There is a different way of trying these problems using not this kind of analog machines, but quantum circuits. Again, we don't know if they will be good or not, because all of these heuristics, you need to actually apply them and try them out in practice to see if they will work well or not. And we don't have the hardware to actually try them for big enough problems. So it's still an open question of how all these heuristics will work. But there is one part of optimization where we can actually prove things. It's very similar to the classical case, and this is convex optimization. So what happens when you have, for example, a linear program or a semi-definite program, or when you want to do like a conic, second order conic programming, which is interesting for things like support vector machines or for portfolio optimization, right? And there, the quantum computer, we can prove what the quantum computer can do because we can look at some more mathematical algorithms, things like how do you do interior point methods for solving linear systems or linear programs or semi-definite programs. And if you see, if you really go at the core of all these methods, what you do over and over again is actually solving linear systems of equations, right? If you want to do all these things, it's iterative methods, you solve linear systems. And solving a linear system is, again, inverting a matrix, and inverting a matrix is something that has to do with the eigenvalues, right? If I knew the eigenvalues, I would just take the 1 over the eigenvalues, and this will be my inverted matrix. So again, this falls into the category of the linear algebra things that the quantum computer can do well. And this is actually one of the most interesting as well quantum algorithms out there, which is that the quantum computer can solve systems of linear equations in many times much faster than a classical solver. Again, not always, because these things, we need to be careful. They depend on things of the data, as we said, but in many interesting cases, we should expect that the quantum computer can solve these linear systems. Not the quantum computer that we have today. This is kind of like, say, a mid-term application, because the quantum algorithms are still a bit complex. Okay, I had something about, as I said, convex optimization, stochastic PDEs. Again, all these numerical methods at the core, they have these linear systems. These are actually nice linear systems for the quantum algorithms. So this is an area where we can expect things to happen. I'm going to skip the security against quantum computers, but feel free to ask me if you want. And I just want to conclude with some prospects and challenges, as I said. So I think I hope I made it clear to you that there are some very powerful quantum tools that we have developed, not only us, but the whole community, that have to do with linear algebra, with sampling and Monte Carlo, stochastic processes, optimization. They're very subtle many times. Like, it's not a clean-cut thing that give me your problem, I will give you the quantum algorithm that always solves it better, right? We need to be very careful how to use it and where to use it, but we are coming up with many particular cases and particular use cases where we can prove or we can see the advantages, okay? Some promising directions, especially for your area, machine learning, Monte Carlo simulations, portfolio optimization. And the last thing, I want to say that, you need to see if all these things will work in practice to some extent. And to do that, you need to test them and you need to simulate them. And the quantum algorithms will be becoming better and better the moment the hardware allows us to actually try things out. There's the same thing with neural networks. The neural networks are much better today because we can try many different things and figure out what are the right architectures than it was 20 years ago, where the ideas were there, many of the important ideas were there, but somehow we didn't have the capability of running these very, very large scale simulations, okay? So I still think that finance and this risk management and risk calculations is something which is a very interesting area for quantum, because many of the core quantum techniques can be applied in this area. It's not going to be easy, right? And it's not going to happen today or tomorrow, but it's certainly worth pursuing. And there are many reasons to make this pursuit worthwhile. So thank you all very much. I think I'm a little bit over time, but I'm happy to take any questions that you have.
This is Robert. Just a question, if you can comment on getting classical data in a quantum computer for applications like machine learning and linear algebra.
Yeah, very good question. So, so the question is, 99.9% times that you want to use machine learning is on classical data, right? So you have your classical data, it could be time series or images or whatever you want. How do you take this classical data and use it into a quantum computer? Somehow you need to translate this classical data into quantum state so that you can do all these interesting quantum algorithms and, afterwards, or quantum neural networks and things like that. So we have come with some quite interesting and optimized ways of doing that, where we can map a classical n-dimensional vector, let's say, into a quantum state that kind of corresponds to this n-dimensional vector in a quantum circuit whose depth is logarithmic on the dimension. Okay, so this is what we call the data loaders. I mean, you have to read your input once, right? Like you need to read the data, right? But then every time you need the quantum copy, let's say, of this data, then the quantum circuit runs a logarithmic number of steps to create this quantum state that could be the input then to your algorithm that checks the similarity between the data, or that tries to do linear algebra with this data. Okay, but sorry, just one more comment. The depth of the circuit is logarithmic, but the number of qubits is the number of dimensions. Okay, so what we can do, what we hope to be able to do in the next 2 or 3 years, is to look at data that have up to 1,000 features, right? These we will be able to load them in 10 steps, right? And then start doing computation on that. Okay.
Just a question following up on that. So that loader, you call it that circuit of depth logarithm of n, is that the same no matter what the input is, or you have to change? I change my input. Do I have a different circuit to do that, or?
Yeah. So
okay.
So it is, how we call it. It is a parametrized circuit, right? Where each parameter of the circuit, let's say, corresponds to some parameter of your data points. Okay. So let's say that if you have 2 data points and you just want to do the linear product and you've never seen them before, okay, then the time that you will spend is linear on the size of these data points because you need to read them. Okay. But now imagine that you have 2 matrices, right? The time to pre-process the thing is the size of the matrices, is n squared, let's say. But then when you would want to multiply them, right, it will still be an n squared computation. Right? Because you need to read the matrix to prepare your circuit, right? And then if you want to use the same matrix many times, like with many data points, let's say this is your weight matrix, let's say, and you have many data points that you want to multiply the same matrix with the same, with all the data, then you don't need to reload it every time. Okay.
Okay.
So this is not, let's say, the optimal way of doing it, but it is a way that is good enough in the sense that we can do it now, right? And it allows you to get the speedups that you will get from the quantum algorithm afterwards. So I'm not claiming that this is where you will get your quantum speedups by just loading this data. It's just that the way that we are able to load the data will keep whatever speedup, whatever quantum speedup we will have afterwards for something like applying a Fourier transform, let's say, or applying some other quantum operation that needed this data to be in a quantum case, in a quantum state.
So yeah, okay. Just what I wanted to understand is that circuit. So suppose so I have the matrix or whatever, something I want to reuse, but in order to load that particular matrix, do I have to? Does each matrix have its own unique circuit, or it's some generic?
Yes.
circuit? So I have to figure that out. How many steps does it take to figure out the circuit?
The moment that you just need to read the data once, even in a read once way. So the way I see it more is like, imagine that the data comes, right? You imagine that you have time series data and data points arrive. you need to pre-process the data, but by just spending long time for each one of the coordinates. So you're spending linear time on the data set, and then you have everything you need to run the quantum circuit.
Okay.
Okay.
All right. Thank you.
But the thing, I mean, just to be clear, you need to be able to read the data. Otherwise, you will be using less data, right? So the quantum computer cannot, do anything if you don't read the data once. But what I'm saying is that we can do it by just reading the data once and not spending any more time pre-processing any of this data.
Okay. Thank you.
So can I ask another question? So suppose I have a qubit that makes a mistake with probability 10 to the minus 3.
Mm-hmm.
Now, if I can take a second qubit that's independent of that, I could run it in parallel, and then if they agree, then I know that that's only going to be wrong, 10 to the minus 6 probability. And when they disagree, then I need to run one or both of them again independently.
Mm-hmm.
So that would seem to give a relatively easy way to increase the accuracy. So what's wrong with that? Is it getting them to run independently that's the problem, or what's wrong with it?
Yeah, very good. So there are many different ways of trying to error correct, let's say, quantum bits, right? So here is a case where what you're saying is not going to work. For example, imagine that what my circuit is supposed to do is sample from the stochastic process, right? Then I'm sampling from a distribution. So sometimes I should get a 0 and sometimes I should be getting a 1, right? And I'm actually trying to calculate the probability of getting a 0 and a 1, okay? Now, if I do this 2 times, right? Then somehow if there is a mistake in this probability distribution, it's not so easy to check which one was correct and which one was not correct. So what I'm saying is that if your circuit has a deterministic value, like you know that it should always be 0 or it should always be 1, it's just that you don't know which one of the two, right? Then you are right, you can run it 10 times and do a majority vote at the end somehow, right? So in some cases, the simple repeat and aggregate could actually work, right? For other things, it doesn't. If what you're expecting is sampling from a distribution at the end, then it's not so easy to check distributions, right? But in any case, I want to say that we do know on how to make fault-tolerant computers, in the sense that people have devised these error correcting codes that basically say that if the error per qubit is below a threshold, then I can use error correction to make it almost 0. It's just that the noise of the single qubit right now, it's not just there yet, right? So that's why we say in the next 3 years or 5 years, actually even recently there was the first paper that said, I can create a logical qubit, like an error corrected qubit, which is better than the qubit itself. So it was the first time that we showed that you can improve a little bit on the quality of a qubit by using 5 qubits together as 1 qubit.
Do we have any more questions? Once, going twice. Well, then let's thank the speaker, Iordanis. It was great.
Thank you very much.
Clearly, everybody
I know
did.
It's a lot to grasp, but I think we will be hearing more about quantum in this field in the next coming months and years. So yeah, I'm happy to talk to all of you.
We're looking for it. So this is you are in a distinguished position, the closing talk of the semester. So thank you for that.
Fantastic.
And to you and to everyone in the CDAR community, wish you a fantastic holiday. And we'll be back online next semester and also in person next semester. Maybe you're close by, Iordanis, right?
I come often. I'm based in Paris, but our main offices are in Palo Alto. So I go between the two, and I always come to Berkeley. I still have friends and people there that I know.
Yeah.
So yeah.
Paris is a good spot. Anyways, I hope to meet you in person before
Same
too
here.
very long. I think we'll be planning to be doing some in-person talks next semester as well as some virtual ones. So happy holidays, everyone, and see you in the new year. Thank you. Bye now.
Bye, everyone.